Hello, everyone. Welcome to join Innovative TechTalk today. And we are happy to have Dr. May Choi, Associate Professor from Department of Civil Engineering to moderate this session. Dr. Choi, please.
Thank you, Kai, for the introduction. Good afternoon, on-site and Zoom audience. And I'm happy to be the MC and the moderator of the talk today. So TechTalk, it's a series of forums and dialogues given by engineering researchers of diverse academic backgrounds to share their insights on innovation-related topics. Today, we'll have Professor Chuyang Tang from Department of Civil Engineering to present his research. So Professor Tang has about 20 years of experience in membrane technology, water reuse and desalination. He has published more than 300 journal papers. It has an H index of 86 from Web of Science. His R&D has received way too many prestigious awards and recognitions for me to mention in details here today. All I can say is impressive and amazing. So now, without further ado, let me pass the time to Professor Tang to present membranes for water and beyond.
Thank you. Can you hear me? Okay, that's good. So thank you, May, for the nice introduction. And it's my honor to present this tech talk on membranes for water and beyond. Now, in the famous poem, Samuel Coleridge wrote, water, water everywhere, and not a drop to drink. Now, with the fact that 80% of people living in water-stressed area, water scarcity is nowadays one of the grandest challenges of our time. There's about 4 billion people experience at least 1 month of water scarcity in over a year. And climate change further adds more uncertainties. So how can we deal with it? Now, Singapore sets a very interesting example. So if you look at Singapore, the setting is pretty similar to Hong Kong. In terms of population density, in terms of available water resources. Singapore do not have enough water resources. So traditionally, they buy 50% of their drinking water from Malaysia. And because they realize the price, the contract price is escalating exponentially. So what they decide to do is to go for alternative water resources, such as through desalination of seawater and the reuse of wastewater. So if you look at the statistics, at this moment, about 30% of Singapore's water supply is through reuse of wastewater. They call it new water. They give wastewater another life. And another quarter of the water supply comes from desalination of seawater. And going forward, they're very ambitious. They want to knock off this imported water from Malaysia. So in another 30 years or so, about 80% of Singapore's water will relying on either seawater desalination or water reuse. Now, the key technology here is membrane. So if you look at this, this nice picture, basically Singapore collects wastewater from all over the island. They send the wastewater to a centralized treatment facility where membrane kicks in. You can use membrane to remove the dirt, and the treated water can be recharged to reservoirs, or can be used for manufacturing sectors, especially in the semiconductor industry. Now, Hong Kong is facing very similar situation of water shortage. So if you look at the conventional water resources, Hong Kong has rainwater, imported water from the Dongjiang River, which accounts nearly 70% of the overall freshwater supply in Hong Kong. And of course, you on top of those, you still have seawater flushing for flushing toilets. Now going forward, the drinking water service department is basically planning ahead, and now they are talking about desalination of seawater, as well as use recycled water. So for example, here they have this this is getting nowhere. Basically, here you can see the layout of the planned desalination plants in Hong Kong at Chuyang Tang. And this plant, once built, the initial phase will supply 5% of drinking water in Hong Kong. And when it's fully completed, it will provide 10% of Hong Kong's drinking water supply. Now, so as I mentioned, membrane could play a key role in providing this kind of alternative water supplies. Now, there are different membrane processes. You go down from particle filtration to microfiltration, ultrafiltration, nanofiltration, all the way to reverse osmosis. The difference is in their pore size. So when you have a pore size on the micron range, we are talking about microfiltration. And going towards reverse osmosis, those pores are so small, the material becomes dense enough that they start to sieve out dissolved ions. So even ions like sodium, potassium chloride can be separated. Now, when we talk about membrane, one very important consideration is the so-called permeability selectivity trade-off. So usually, when you make a better membrane, more permeable membrane, you tend to lose the selectivity. So if you move in this direction, higher permeability, less selectivity. Or if you want a more selective membrane, you typically sacrifice the permeability. Now, of course, nowadays nanotechnology or biotechnology can give us some kind of inspirations to seek some alternative, better solutions. So there's a lot of different materials being reported. You can, for example, align carbon nanotubes in an array, or you can use natural proteins to do the job. Now, one of our early experience is to use this so-called aquaporings. So aquaporings, aqua means water and poring means channels. Those are naturally existing proteins, and they have this kind of highly defined pores. Highly defined pores with our funnel shape. And at the center of this pore, this size is around 2 angstroms, so which is good enough for water molecules to pass through, but ions would be excluded. Even protons will not be able to pass through this kind of channels because of the charge regulation. They have this kind of charge regulation here, which will repel protons. So if you look at this kind of channels, it's amazing. For a single channel, every second, it can pass through 3 billion of water molecules. Now, if you compare our best commercial membranes, best reverse osmosis membranes, the natural proteins are about 100 to 1,000 times more permeable. So they are amazing. And if you look at the selectivity, they are nearly perfect. They have nearly perfect selectivity. So we are inspired by this kind of materials. Our group is probably the first team to use this kind of materials for artificial membranes. So basically, we incorporate aquaporins into this so-called vesicles. So we can make a lipid bilayer, or we can build this kind of so-called ABA block copolymers, which can allow aquaporins to self-assemble into the vesicles. And then we can incorporate these vesicles into our artificial membranes. So for example, here you can see based on our CFD simulation, once we incorporate those aquaporin-contained vesicles, they can channel water at a much higher efficiency. So water can pass through our synthetic membrane at much higher rates. And on top of that, that can also boost the selectivity of the membrane. So we spent about 3 years working on such a project, and it was very lucky that we patent this technology. Indeed, our patent protect us in more than 20 countries. And a startup company was established it's called Aquaporin Asia. If you are interested, you can see a bit more into this company's profile. And this kind of product was also taken into the space for water recycling. Of course, I mean, they are still testing this. You know that taking water to the space is very expensive. So recycling water in space is also a very interesting topic. This company is still working on that. Besides aquaporin, we're also interested in other materials. For example, well, I mean, if you talk about natural proteins, of course, you worry about the stability of this kind of material. So one idea is, since we only need this pore region rather than this entire entity, so why not we make synthetic channels? Now, my group is not really specialized in materials per se. So we decide to collaborate with some other groups. There's one group in France. They're specialized in making this kind of synthetic channels. So we're trying to build a project together to incorporate synthetic channels into our membranes. Now, besides these amazing materials, we do also look at conventional materials. So in the field of reverse osmosis, for those people who are familiar with reverse osmosis, we know that polyamide is a standard material for desalination. So basically, to make a polyamide, we make a cross-linked polyamide. We use two monomers. Those are very classical chemistry. This kind of chemistry was invented 40 years ago. But nowadays, this is still the best chemistry for making reverse osmosis. Now, basically, we take two monomers. One is an amine monomer and one is an acid chloride monomer, and they react at an interface. They make this kind of cross-linked polyamide. But the amazing thing is that if we trick this chemistry a little bit, we can make it so much more efficient. So for example, here we notice that this reaction produces an acid and also produce some heat. We discover that if we put in some additives in this reaction, for example, if we put some bicarbonate into this reaction, now bicarbonates can react with proton, and that will release carbon dioxide, CO2, under heating, so that gas will be released. And those released gas will form nanobubbles. So when we control this reaction, we can form this kind of nanobubbles, and that will make this membrane surface very interesting because you produce this kind of nanobubbles, and these nanobubbles are enclosed by our desalination material, this polyamide layer. So instead of making this kind of flat layer, we make this kind of a layer with nodules. We call it roughness nodules. And that certainly can help us to increase the filtration area. indeed, that also help us to optimize the transport paths. So with this simple approach, we can enhance the permeability of the membrane by almost 10 times. Now, in addition to bicarbonate addition, we can also use co-solvents, volatile co-solvents. So because of the heating, at the interface, we have the heating. So if we have something like acetone, for example, acetone will be vaporized. That can also help us to produce this kind of roughness structures. Now, another thing we are trying is to think about this kind of a 3D printing idea. Now, normally when you talk about 3D printing, the resolution is kind of limited. We are talking about micrometer resolution. But when we want to build this kind of layers, because even the commercial membranes, the thickness, we can already go down to 100 nanometers. So in order to achieve better membranes, we want to go down to below 10 nanometer in thickness. So how can we do it? Now we can actually use a layer by layer additive approach. We can spray those monomers into micro droplets. And if we can choose the concentration of those monomers, so we can control the quantity of monomers delivered to the reaction interface very precisely. So by controlling the volume delivered to the surface, the spraying time, we can build this kind of uniform layer with precisely controlled thickness. So for here, the thinness layer we built was 4 nanometer. So with this approach, the lateral resolution is not so good. The lateral resolution, we're talking about millimeters to centimeters. But the vertical resolution, we can control down to nanometer range, 1 nanometer. So this is very powerful method for us to build different kind of membrane structures. So we are working on many different kind of membranes because of time limitation. So I only show some examples. And in addition to making membranes, we are also trying to establish some kind of standard membrane material database. So we team up with Yale University, with KU Leuven, and with TechTalk to build an open membrane database. So everyone can enter their data into our database, and everyone can retrieve data from our database. So this will also, in future, we hope that this kind of database will allow machine learning, artificial intelligence to find out what will be the optimum material, optimum structure for making membranes. Now I will switch gear a little bit. Membranes can not only used for water production, water purification. Membranes can also be used for generate energy for power production. So in this example, basically you see a river flowing into a sea. Now that between these two type of waters, there exists a huge difference in salinity. And this salinity will translate into a chemical potential energy. So if you compare, for example, a typical hydropower, a dam, to generate hydropower. So this kind of typical salinity difference is equivalent to 250 meters in water elevation. Now, if we can find a method to convert this energy into electricity or some other useful form of energy, then the potential can be huge. So here you can see the global potential for salinity gradient power. We're talking about this potential can be larger than the global hydropower production. Now, one way to do that is through some kind of electrochemical conversion. So for example, if we can have an ion selective material, ion selective membrane here. Then on one side, you have a higher salinity. So you have a lot of sodium and chloride ions. Now, here we make this membrane only conductive to sodium, but not to chloride. So only sodium can pass through the membrane under the concentration gradient, but chloride will be rejected. And in that way, you can establish ionic currents, and you can use electrode to convert the ionic currents into electricity. So couple of years ago, we have a CRF project, and we collaborate with a team from HKUST. That team, they basically established some kind of single ion conducting material, NESCON. So we take their material, process it into membranes, and to shoot for this kind of energy production processes. Now, membranes not only can be used for water, for energy, you can also use them for resource recovery. For example, we can build, if you have wastewater, wastewater contains organics, contains nutrients. If we can design a good membrane process, in this particular case, we use forward osmosis to concentrate wastewater. Once we concentrate wastewater, then we can take some valuables out of the wastewater. For example, we can recover nutrient, nitrogen, phosphorus for agriculture application. Or you can convert the organics into methane or even hydrogen. And then you can utilize the energy. Now, because time limitation, so I have to move on, and I'll just finish my talk with our filter work. Sometime early on, I talk about those dense membranes, which has a very good removal power. But in some cases, you don't want this kind of very dense material because the permeability is very low. Here I show you one example, a highly porous material, such that you can operate this material just with, for water filtration, just with gravity. You don't need electricity. And here I show you this kind of nanofiber structure. You can use electrospinning to prepare this kind of materials. And here you can see that under gravitational force, water can just, you only need 5 centimeters of water height. And that's good enough to operate this kind of filter. And you can clearly see that the filtered water does not carry color, not like the original raw water, very colorful if you dare to drink that. And we also make it into different kinds of filtration device. Now, for those of you who are physically attending this talk, you can see there's a display booth there, and you can see some products there. And we're also trying to make this kind of materials for air filtration into face masks or some other products. Now, I probably take too much time, so I'll just end my talk with a video. Now I'm much relieved. Thank you.
Thank you. Thank you very much, Professor Tang. I think